Hello, my name is Tian. I am a ship intern working under Dr. Peter Bocage at the NIST Center for Neutron Research. Over the summer, I developed a web app and database to help manage and streamline the sample preparation process for a robotic chemical mixing platform being developed by the Material Measurement Lab and the NIST Center for Neutron Research. Through the app, users are able to view, edit, and create entries in the database while also printing out physical barcode labels for each sample. The app has a variety of features, such as file export, remote entry, and interactive charts. My project involves a robotic chemical mixing platform, shown on the right, that is being collaboratively developed by the Material Measurement Lab and the NIST Center for Neutron Research. This platform is used to automatically create complex liquid mixtures with relevance to industries from personal care products to biopharmaceuticals and even COVID vaccines, and then analyze the structure of those mixtures using small-angle neutron scattering, SAND, and/or small-angle X-ray scattering, SAX, for phase stability mapping. The ultimate goal of all of this is to have the data generated from SANs and SACs on the samples made by the robot to serve as a reference dataset for training machine learning networks to process and classify scattering data. We currently prepare samples for the robot to make in a very ad hoc way. First, you manually calculate a target composition, weigh out reagents into containers, write the weighted quantities onto a post-it note, and then type the weights back into the computer when the container is loaded into the robot. This process has lots of potential issues. The manual nature of human input means that this process is very slow. When the quantities are typed back into the computer for the robot, there is a chance for typos, which would cause the robot to have the wrong details about a solution, which could also impact other samples created by the robot using said solution. There is also a lack of traceability in the process. Ideally, we would like a way to be able to track errors in the system. For example, if sample X was made with Y and Z, and Y was made incorrectly or had problems, we would also be able to know that X may have also been compromised. Since currently everything is physically written down, there's no quick or centralized way to find information such as what solutions were used to create a certain sample. My project was to help create a more robust solution using databases and web user interfacing. The goal was that through a web app, a user can enter a target composition and then have the system automatically generate a unique container ID and then print a label with basic information and a barcode. The user would then be able to weigh the reagents in and then update the web database entry with the exact composition, and then when the solution is loaded into the robot, they simply refer to the container by its ID via scanning the barcode, and then the robot is able to automatically source composition from the database. Each database table has its own page that allows you to view, create, and update entries. Here's the general view for the component table with real data as an example. By default, the web page displays separate entries for whatever you're viewing, in this format where they are listed separately by name and ID, and further more detailed information is listed below in an individual table. There are buttons for exporting everything to a CSV file, viewing a JSON representation of the data, and editing entries. All of these entries are paged, and you can adjust how many entries are on each page. You can also toggle a unified view exclusive to component that puts all of the information in one table and also gives you some extra filtering options. Creating and editing entries is a page where you're given forms to fill in for the cells of whatever table you're making an entry in. Depending on what you're creating, these consist of free text and drop-down menus. For the stock and sample tables, you also have an alternative creation option in addition to the single entry that you just saw. Here, we can specify any number of components or stocks to add, along with the percentage of the total quantity, which is either in grams or milliliters. After being created, stocks and samples have detailed views that list the information about their respective components or stocks, such as the amount added and units. There is also an interactive chart that visually displays the proportions in the composition. You can also upload and download CSV files for all views. In the image below, I've downloaded all of the component entries. Each value corresponds to the header at the top of the file. When uploaded, entries will be created or updated as necessary. The app can also display a JSON representation of all or individual entries in the format like the image on the right. To remotely send data, you would just need to make a post request, like in the above image, to the corresponding URL for whatever entry type, and then the app will treat it as if it were a manual entry. This allows for database entries without the use of the user interface. When viewing stocks and samples, there's a button for printing labels. When this button is pressed, a label image will be generated similar to the one below, which is then sent to the label printer. In this example, we have a label for a stock named Stock Test that has an ID of 1 and was printed on July 22nd. The QR code contains the ID of the stock or sample for the robot to read. The ID, type, name, and print date are in text on the label. Currently, the web app is running on Nisto Roboto, the Linux machine that also manages the servers for the robot autopipetter and pump/flow control. With that, I'd like to thank my mentor Dr. Peter Bocage and also Dr. Tyler Martin for helping guide me on this project and providing me design feedback. I would also like to thank everyone at the NCNR, including the internship directors Dr. Julie Borchers and Dr. Joe Dura.